Modern legal discovery involves processing terabytes of unstructured text, emails, and financial records. To make sense of this volume, attorneys need the reasoning capabilities of large language models. But the moment you attempt to deploy those models, you hit a wall. You have a strict operational paradox. You need massive computational intelligence to parse the evidence, but the evidence itself is protected by attorney-client privilege, NDAs, and privacy regulations. Routing unencrypted case files out of a secure environment and into a commercial cloud AI provider violates baseline confidentiality. It exposes proprietary data to external network vulnerabilities. If you attempt to upload a sensitive legal PDF to a centralized cloud provider, the operation is flagged and blocked entirely by internal compliance protocols. Maintaining absolute data sovereignty requires moving the compute to the data, rather than the data to the compute. This demands a completely offline, zero-trust architecture. We call it LexVault Mesh. The physical constraint of a localized system is that it must run on the devices you already own. This is a bring-your-own hardware environment, relying strictly on standard consumer-grade smartphones, laptops, and desktops. The intake process begins at the absolute edge of this network. Usually, this means a mobile device used in the field to photograph or scan physical evidence. Starting in the top left of this architecture diagram, the capture and input block executes optical character recognition entirely on the smartphone's local processor. Extracted text then flows directly into the evidence ingest module, formatting into a machine-readable payload. At this point, we hit a hardware limit. A standard smartphone lacks the video RAM required to run large vector embeddings or operate complex reasoning agents. Since the phone cannot execute large language models natively, it has to offload the heavy computational work to the larger local devices nearby. Therefore, capturing evidence at the edge mandates a method for secure compute delegation. The device must pass the payload to stronger hardware without ever routing a single byte through an external internet connection. To handle this local delegation, we use a specialized orchestration layer known as the QVAC SDK. Looking back at the architecture flow, the SDK establishes a secure peer-to-peer mesh network, connecting available local hardware into a unified cluster. The ingested payload toggles safely across this localized P2P connection, landing inside the mesh intelligence block. In a conventional setup, this handoff would involve making a call to a centralized server API over the public internet. By replacing the external API with a localized P2P handshake, the system achieves total network isolation. There are no open ports and no external attack vectors. As the devices connect, the QVAC SDK constantly monitors the available CPU, GPU, and RAM across all active nodes in the room. This enables a process called hardware-matched delegation. The system analyzes the specific requirements of an incoming task and automatically assigns it to the device best equipped to handle it. The SDK operates as a localized control plane. It coordinates standard, offline consumer electronics into a secure, sovereign intelligence cluster. The first major workload in this pipeline requires generating embeddings to index the text. Returning to the diagram, the system routes this mid-tier workload to the laptop. A standard laptop GPU is highly efficient at handling retrieval-augmented generation, or RAG, operations. Here, the evidence agent reads the ingested documents, mapping out individual actors, dates, and entities. But mapping these entities is relatively lightweight. When it comes to cross-referencing thousands of data points to find logical anomalies, the laptop's compute resources hit their limit. The system executes a secondary handoff, pushing higher-order tasks to the desktop. Here, the contradiction agent evaluates mapped actors against the timeline, searching for inconsistencies. Notice the arrows forming a continuous asynchronous feedback loop. The laptop retrieves context, and the desktop reasons through it. By segmenting these distinct agentic workflows and matching them to specific hardware profiles, the network maximizes token throughput while keeping every piece of data strictly local. Distributing tasks across different physical machines presents an immediate technical hurdle. Without a centralized cloud database, these isolated models need a way to maintain a shared understanding of the case. These local devices have to operate like a flawlessly synchronized engine, passing critical state data seamlessly back and forth. The network manages this by packaging the necessary variables into serialized context windows, which are then transmitted over the P2P connection. Because the laptop generates dense, efficient embeddings, the actual file size of these context footprints remains exceptionally small, ensuring they transfer almost instantly. This speed is a hard requirement. If passing context between devices takes too long, the models sit idle, failing the system's latency constraints. To prevent idle time, the delegation is completely asynchronous. While the desktop agent spends seconds churning through a complex contradiction, the laptop is already preparing the next batch of embeddings. The intermediate outputs are held securely in localized memory states on each device, waiting until all agents have fulfilled their specific parameters. Managing this state data locally ensures the network doesn't throttle itself. It allows continuous, uninterrupted multi-agent processing right at the edge. This diagram concludes with the convergence phase. Once agents analyze the evidence, outputs flow into the green synthesis block, formatted into a visual knowledge graph and text-based chronologies. These components merge into the final deliverable, a heavily annotated litigation bundle generated entirely offline. But generating a bundle isn't enough for legal tech. The system must provide strict auditability and verifiable performance benchmarks to prove it works reliably. To guarantee transparency, the framework automatically generates reproducibility logs for every session, detailing exactly how the models performed. The critical metrics here are the low time to first token and the high throughput in tokens per second. These numbers confirm that standard consumer hardware, when networked efficiently, reaches enterprise-grade inference speeds. LexVault Mesh takes fragmented, highly restricted evidence and structures it into actionable case knowledge. It proves that sophisticated, multi-agent AI reasoning doesn't require a cloud connection at all. It simply requires the right architecture.